Morning, sir.
Hey, good morning. How are you doing?
I'm good, sir. Sir, last week, the homework I had submitted on the assignment section in Canvas instead of giving you
Okay.
a printed copy.
Yeah, okay.
Yes, sir.
So
I'm
it's
just
up,
making
it's you uploaded it to Canvas,
Yes,
right?
yes.
All right. Yeah, we
Because
printed it.
there were portions which were handwritten and other portions which were typed. So
Okay.
it would become a little bit of a confusion. I gave you.
Sure, no problem. Yeah, you can turn it in electronically as well.
Yeah, I have talked to you on LinkedIn.
Okay, because I think,
Yeah, and then last week during the Study Association. Yeah.
so what's your name?
Which one?
Oh, so you want the Zoom?
Yeah.
I was thinking, so I don't know much. Yeah.
Next one.
Next one is not so research.
No, I'm going to the last one.
How's it going, Shisha?
It's okay.
Figuring out that stutter geometry?
Yes.
All right. How are you guys? Good. Good. Everything going well? Ciao, fans. Actually, worry that. All right, guys, it's 9:30. Let's go ahead and get started. Okay, as a quick reminder, remember that we have a updated course schedule for one of our lectures. This is our webpage, right? The Canvas webpage. And I put in here in blue the exact change, right? So on October 24th, which is like a month from now, make sure you come to toward 10:30. It's across the hall. And we start from 8 at 8. We go to 9:15. Of course, everything's recorded. If you cannot make it, then there will be a recording on there. It's also updated in our schedule for our syllabus. If you download the syllabus, then on that date, it's also indicated there. So class is from 8 to 9:15 and toward 10:30 on the 24th. And I'll remind you every lecture until then, so you'll for sure not forget. Okay, so that's a month from now. So where are we at now? We are here, lecture 10. So let's get into it. Any questions from last time? We're gonna review, so don't worry. Okay, so we solved the wave equation in rectangular coordinates. Now we're moving on to cylindrical coordinates, right? There are three main coordinate systems that we're gonna utilize in electromagnetic theory, and that's rectangular, cylindrical, and spherical. You guys have seen these before. We're going to now move on to solving the wave equation. What kind of wave functions exist in the cylindrical coordinate system that have variations that depend on rho, phi, and z, right? And why would we choose a certain coordinate system over another? It's because it's easier to apply the boundary conditions, right? We have to do two things to solve for the electric and magnetic field. We have to solve the wave equation, maybe inhomogeneous if we have a source, or maybe homogeneous if we're trying to find or define modes that can exist in the system. And then we need to apply boundary conditions to reduce the solution's unknown coefficients and find the eigenvalues, right? The wave numbers. So we need to do those two things. Now, if a geometry is cylindrical in shape, coaxial cable, for example, then it would be much easier for us to apply the boundary conditions in cylindrical coordinates because we can just specialize our solutions to rho equal to A, for example. That puts us on the boundary where we need to apply a particular boundary condition. So that's the idea. Now, of course, we're solving Maxwell's equations under the guise of time harmonics. We're assuming a temporal distribution or a temporal dependence of e to the j omega t. Therefore, we expect by linearity that we should also get some kind of harmonically varying wave functions, right? In the cylindrical coordinate system, as we saw, we're going to derive three. There's going to be the exponentials that we're familiar with. An azimuth in the z-axis, it's the same as a rectangular coordinate system. We're going to have traveling waves and standing if we have some sort of boundary conditions in the z direction. And we're going to end up with a new function, which is called a Bessel function. We're going to derive those today. All right? Okay, good. So first, let's find out what is more difficult about cylindrical coordinate system than the rectangular coordinate system. So we express our electric field in the cylindrical coordinate in terms of the cylindrical variables, rho, phi, and z. And we have rho hat, phi hat, and z hat components. These three scalar functions themselves, if you plug in a coordinate in space, define a component of a vector of which you can construct by adding these three orthogonal vectors, right? Okay, that electric field, we substituted into the wave equation. And what we see is del squared operating on the electric field is equal to negative beta squared operating on the electric field, right? Multiplied by the vector field. So here, let's just work the first term out. We have del squared e rho hat, right? We remember if we, okay, so I fixed this slide from last time. Remember we had the incorrect Laplacian, but now I've corrected it. So here's a Laplacian in cylindrical coordinates, and we're gonna work on the first term here. These are spatial derivatives. They operate on what you might forget when you first go to solve this problem, on a product of two functions. A unit vector is a function, right? Technically, I can write this unit vector rho hat. What happened? Okay, sorry. I can write this unit vector rho hat as a function of rho, phi, and z, right? What are the two defining properties of a vector? Magnitude and direction, right? So what makes two vectors equal is if their two properties are equal. If I have the same magnitude and same direction, but I'm at a different point in space, then those two vectors are considered equal. Therefore, this vector rho hat might depend on rho, phi, and z. If this vector does not change as I change rho, phi, or z, then that vector is constant, right? For this coordinate system. Okay, good. So if we expand each of these derivatives by using the product rule, then we'll end up with the following terms, right? All of these terms. So we'll see now we have derivatives of unit vectors. And you guys remember from your homework 1 that you calculated some of these, right? And that was the reason why you did that in that homework. So you could understand, you could visualize how these unit vectors depend on coordinates in coordinate systems. So here we have the derivative of rho with respect to rho. So rho, say I'm the z-axis. Rho points out, right? So that's saying rho points out. Now, if I change my variable rho, this vector is not changing its length, it's a unit vector, and it doesn't change its direction, right? It's still rho directed. So this term goes to 0, right? How about, okay, so here's another rho hat rho. How about rho hat with respect to phi? So now I'm still the z-axis. Here's my rho hat unit vector. I'm going to change my angle phi. The length is not changing, but the direction is, right? So this vector is not constant with respect to rho. this derivative matters, right? And then of course, rho hat is the same with respect to z. So this goes to 0. The whole moral of the story is you cannot distribute the Laplacian operator into the unit vector, the electric field like we did in rectangular coordinates. And that makes our life a lot more difficult, all right? Okay, so how are we gonna deal with this then? Okay, so we can't just distribute the Laplacian. What we're gonna do is we're going to rewrite the Laplacian in terms of this vector identity, right? You guys also did this in your homework 1, which is used a lot in electromagnetic theory. So we're gonna replace del squared with the following using the vector identity that you studied. So the wave equation now is here, all right? Good, okay. So now what we can do is we can plug in our assumed electric field form in the cylindrical coordinate system into this wave equation. So there are a lot of vector calculus operations that you have to turn the crank and do, right? But it's just tedious work. Take the curl of this E, and then take the curl of that result, take the divergence of this E, and then take the gradient of that result and piece it together, right? You kind of did that when you did the proof of this theorem in homework 1. Anyway, so you may or may not have this in your homework. We'll see, your homework's coming out this Thursday, but you may have to do this, all right? Anyhow, what you do when you do that is you get these 3 equations, right? So the whole point of substituting in this vector result into the vector PDE is to separate it into scalar PDEs. There are a couple of different steps that we need to take to solve the wave equation. With vector PDE, we need to derive scalar PDEs first, like we did in rectangular coordinates. Then we need to derive ODEs, which these each couple into 3 ODEs since it's a 3-dimensional coordinate system. Then we need 3 ODEs, then we can solve ODEs, right? We use separation of variables to do that. Okay, in cylindrical coordinates, if you do all these operations, you end up with these two expressions in this one, right? So there are 3 still scalar PDEs, but the problem is these 2 are coupled now, right? So these are difficult to solve. There are equations like 3x plus 2y equal to 5 and 6x plus 7y equal to 10. 2 equations, 2 unknowns. You know how to attack that problem. But you just have calculus operations instead of linear operations, algebraic. Okay, but these are difficult to solve. We're going to avoid that. We're going to solve this one here, all right? In doing so, we end up with a set of wave functions, Bessel functions, azimuth, and exponentials, as we saw last lecture. However, if we want to utilize those expansions, those harmonic functions to represent our electric field or our magnetic vector potential, electric vector potential, magnetic or electric field, they have to be z-directed quantities. That's one restriction of solving this one only, right? We're solving this form of the wave equation for a z-directed field component. So whatever problem we're solving in electromagnetic theory, using this construction of the Bessel functions and so forth, has to solve for a z-directed quantity. However, as we'll see, you can use vector potentials in the z direction. And we know that from your previous course, and we'll go over it again in this course, that B is equal to the curl of A. So you can get orthogonal components to Z in the electric and magnetic fields by making one of these a potential. So we'll see that later too. Anyhow, so don't feel restricted by it is what I mean. You solve problems where you use a particular mode set, which is called TE to Z or TM to Z, or you can make combinations of these modes, right? So you still have a lot of power. Okay, good. Any questions? All right, so still reviewing from last time. All right. So as I was saying, we have this wave equation that we're solving, but we have to solve for a z-directed quantity, right? That z-directed quantity could be electric vector potential, and we'll see that later in the course. A magnetic vector potential. In that case, you'll get TM to Z modes or TE to Z modes. Some examples here are cylindrical waveguides where you would use this approach with this assumption for psi. A z-directed electric field. We'll see this at the end of the course, where we have scattering by plane waves by cylinders with the axis along the z-axis, or a z-directed magnetic field, so we can have TE to Z scattering by cylinder, right? But notice all these quantities are z-directed, all right? Okay, so now we're going to do our separation of variables process like we did in rectangular coordinates. We assume psi can be represented by a superposition or a multiplication of or a product of three scalar functions, or sorry, three functions of a single variable, right? What was the strategy to do that? Because if this assumption holds, if our electric field, any of these can be written in this product form, then this PDE, the scalar PDE, will separate into three ODEs. All right? Okay, so del squared FGH, so we plug in FGH for our assumption for psi, we get del squared FGH minus beta squared FGH. We substitute in for the Laplacian, and then we distribute FGH into all of these terms, and we end up with the following expression, right? Then we do the same thing. This is all the same exact steps that we did in more detail in rectangular coordinates. Now we're going to divide through by FGH. The right-hand side does not have FGH. And what we do there is we start to see terms. So first off, remember this expression here, this string of functions, has to equal to a constant at the end, right? Therefore, if a function is, or if one of these terms is a function of only one variable, and no other term has that variable, then it must be a constant, right? So I think we talk about that on the next slide. Yes, so I repeated it here at the top of the slide. Notice that the last term is a function of z and no other term is a function of z. If this expression has to equal to a constant, let's say that this term ends up not being a constant, 1 over h d2h dz squared. If that isn't a constant and ends up being a function of z, maybe 2z, z squared, then there better be another term that has a way to cancel that function, right? Minus z squared or minus 2z. So that the whole thing can equal to a constant at the end. But there is no other term that depends on z. Therefore, this term has to be a constant, right? So the first step, we can get one separation constant by assuming that this term is equal to a constant, right? We're going to call that constant beta z squared and negative for reasons that we understand now, but we'll see as well later when we do the rectangular coordinates. So the constant is called beta z squared. It's called a separation constant. If we rewrite this, we can multiply both sides by h. d2 squared or d2h by dz squared is minus beta z squared h. And that's easy to solve. We solved that 100 times, right? What's the only functions that we can write down that if you differentiate twice and add back to itself, you get 0. Or not 0, you get, you get 0, right? Sine, cosine, exponentials. So they're harmonic functions. And that's what we expect, right? We are assuming the temporal dependence is harmonic. And since Maxwell's equations are linear, we'd expect that our spatial dependence also takes that same form. So think about it like this. I have a source here, right? This is some current, it's oscillating here. And as this current oscillates, it's gonna fill the room with electromagnetic waves, right? Like when I turn on the light switch in the back of the room, the whole room fills with electromagnetic waves, visible light. Now, if this source is varying sinusoidally, perfect one frequency, right? At so many gigahertz, it's varying sinusoidally, then the waves that it produces because of linearity, all the vectors in that electric field also vary with that same time dependence, right? They vary harmonically. And therefore their spatial distribution or spatial dependence will also be harmonic, right? So we expect that. Okay, good. So we have this separation constant. Let's substitute it in for this term because we've made this equality now, right? We made this equality, so we can replace this term with beta z squared, and that's what we've done here, okay? Now, this is the same exact equation, except we've substituted in a separation constant and we divided through by rho squared. By dividing through by rho squared, we identified another term which depends only on one variable. This term is the only term that depends on phi, and it still has to equal to a constant. So that one we're going to set to minus m squared. And we'll have another expression that has harmonic functions as solutions. Exponential sines and cosines. Okay, so this whole expression has to equal to 0 at the end, right? This term is the only term that has phi in it, yeah? So let's say this not equal to a constant, contradiction. Let's say it's equal to some function of phi, say phi squared, right? How can phi squared plus some other terms equal to 0? And if these terms don't depend on phi, right, you'll end up with phi squared at the end. It can't equal 0.
It could be a function of phi.
This term, but g is only a function of phi, right? By the separation assumption. G is only a function of phi. And this is an ordinary derivative.
What is this compared to? Homogeneous
Yeah, very good. So this, what we're solving here is the homogeneous solution, which was the complementary solution, right? The homogeneous solution in this context tells us what modes are possible, what field configurations satisfy Maxwell's equations when we recast it in terms of the wave equation, right? So these are the possible wave functions that you can then expand solutions in terms of. And I think I showed you before, but we didn't go deep into it, right? Which was eigenfunction expansion. If I know the eigenfunctions of some operator, it's a differential equation, right? Then I can expand and resolve the homogeneous equation to get those eigenfunctions. If I have an inhomogeneous differential equation, I can expand the left-hand side in terms of those eigenfunctions because they solve that differential equation, and the right-hand side in terms of the same eigenfunctions with unknown coefficients, eigenfunction expansion. And then I can use the equality to solve for those coefficients. So just to show you, if we can get back to that. Here, whoops. Here, so we solve this wave equation, right? In rectangular coordinates. We end up with, then we're gonna solve, we end up with the wave functions, right? That we get from that. They're eigenfunctions. So here's a wave equation that's inhomogeneous. We expand both sides. We solve for the wave functions that satisfy this homogeneous differential equation. Then we expand both sides in terms of them. The electric field, we expand in terms of these that were the solution to the homogeneous equation. And we can also expand the right-hand side, but in this context, we don't need to. We just take the dot product, we project these, we expand, basically it's the same thing. We expand the right-hand side in terms of these wave functions. By projecting the current functions. Yes? Do you have a question? Okay. Okay, good. Anyhow, you can look at that if you want. When we get to solving an inhomogeneous wave equation, we're not going to take that approach. We're going to solve it by the method of Green's functions. Okay, good. Now we have another separation constant. Let's plug it back into the differential equation. And we're going to let beta squared. So remember, we have the separation equation that we get at the end, right? In rectangular coordinates, it was beta x squared plus beta y squared plus beta z squared is beta squared. Here we're going to have beta rho squared plus beta z squared is beta squared, all right? And you'll see why. The reason why is because this is not an independent separation constant. It links, the way that this works out is the final differential equation that we have to solve, the third one, that's the rho dependent, has that separation constant in it. We can't remove it. So it's not technically a independent separation constant, all right? And you'll see the wave functions that we derived, the Bessel functions, depend on both beta rho and m. So we'll get to that. So this expression we can plug back in and multiply both sides by f. Now we have a differential equation completely in terms of rho. Of course, it also has a separation constant azimuth in it. Luckily, or maybe not luckily, but probably the first person who solved this, it probably wasn't surprising either because they're in cylindrical coordinates. But for us, it's surprising. The nice result that we get is it's a Bessel differential equation. And that's been solved by mathematicians, right? Great. Okay, so this is still review, right? So Bessel differential equation, we can solve that. Okay, so I'm gonna kind of zoom through this, but you guys have for sure undoubtedly seen this. If you haven't, then I put all the details in here to solve Bessel's differential equation. You most likely have taken a class in differential equations, but we'll go through it anyhow, just in case you haven't. What's important at the end is that you understand how we solve the Bessel differential equation, but more or less how to utilize the Bessel functions themselves, and not necessarily how their series expansion representation is derived, okay? Okay, so here, we have Bessel's differential equation. We know that this, so okay, remember, if we have a differential equation, what is the solution to the differential equation? It's some function, f, right? That has all of these relationships between its different derivatives. So when I solve this differential equation, I end up with some function f that if I take all its derivatives and add them together in this way, I get 0, right? So that function f might be a special function, right? I only have a certain handful of functions, sine, cosine, log, exponential, polynomials, things like that, that I can choose to try to see if they satisfy this differential equation. In most cases, you probably won't, the differential equation won't be satisfied by this small set of classical functions that you can write down, right? So what we have to do is construct new functions that can be any shape, really, by expanding them in terms of a series expansion, right? So for example, f, we don't know what f is, but we're going to say I can represent f however it is in terms of a series expansion, a power series in terms of rho, because this differential equation is in terms of rho. So now I have the ability to construct whatever shape of function I need to satisfy this with all its derivatives, right? But the problem now shifts to finding these coefficients. So why do I choose rho n plus r instead of rho to the n? Because this differential equation has a singular point in it. I don't know if you guys remember that, but if the solution has a singular point, rho equal to 0 is a singular point, then we have to use the method of Frobenius, which is just like a power series to solve the differential equation. We include this extra unknown parameter r, which you have to determine through the solutions process. Okay, so what are we going to do? We're going to assume we can represent whatever function we're trying to construct, piece together in this power series format, and we're going to plug it into this differential equation, and we're going to synthesize it basically, right? By finding its coefficients. So here's the first term, f, and then we have this rho squared d2f, d rho squared, that's this term. And if we take, so we know what f is, we differentiate it twice with respect to rho, and we multiply rho squared, then this is the expansion for that, yeah? Okay, then we have rho d rho df is there, then we have beta rho squared f is there, we have m squared f is there, all right? Plug all of those expansions back into the differential equation. And remember, when we have a bunch of summations and a bunch of powers that are just added together. But what we want to do is find a condition where all the coefficients have to be 0 themselves. And the way to do that is to write this whole thing as one big summation against one power, right? So we need to factor out this summation from all of them. So we have one big summation multiplied into a big expression, one summation, one expression, and then one rho to the n. And that's equal to 0, right? Then the only way that that expression can be 0 is if the whole coefficient is 0. Okay, so how do we do that? Well, what do we notice here? This is the highest power of rho, right? Rho n plus r plus 2. All right, so these are all rho n plus r. So what we want in the end is some summation, some expression, rho to the same power. In this case, rho plus r plus 2 is equal to 0. The only way this expression can be 0 is if all those coefficients are 0, because rho is assumed not to be 0. All right, so we're trying, that's the goal, that's the strategy. We need to construct this kind of form of the differential equation. All right, so rho n plus r plus 2 is identified as the highest power. We need to run off terms in the rest of these series until they have that same power. And the way to do that is, for example, this one here is rho n plus r. We need to get to rho n plus r plus 2, so we need to get to the n plus 2 term, right? So first, let's run off the n equals to 0 term. A0, 0 plus r is r, 0 plus r minus 1 is r minus 1. A0, r minus 1. And then it's rho to the r, because n is 0 first, right? Then the next one is, now n is equal to 1, a1, 1 plus r, a1, 1 plus r. 1 minus 1 is 0, then we just get an r, and then it's rho to the 1 plus r, yeah? Now what we have is this series starts at n equals to 2, which is a problem, we're gonna fix that. But we have rho n plus r. Okay, so when you start that at 2, you get rho plus, you get 2 plus n plus r, right? The way we're gonna make that look the same is we're gonna let s equal to n minus 2. We can do that, right? And it fixes two things. It fixes the starting index here and this power. So we have these terms are the same. S now is equal to 0. Why? Because n started at 2. 2 minus 2 is 0. So S starts at 0. And n is equal to, so from here we can say n equals to S plus 2. So we replace n here with S plus 2. And we have the form that we were looking for. S plus R plus 2 and starts at 0. Now this summation is compatible with this one, right? we can factor out the big summation. They both start at 0. They both have the same power. So now these coefficients here and this one will end up in that big summation, right? That's the strategy. Great. Any questions? So you guys are all, you've seen this before, yeah?
Series converge or diverge to a value.
Does the series converge? That's a great question. Yes, you have to consider that when you use these series expansions, they have to be convergent series, right? In this case, they are convergent series, and we'll make sure that you have to make sure that there's certain regions of convergence and so forth, right? So that's another thing you have to do on top of finding the coefficients. Great question. Okay. Okay, so here we are. Let's do the same thing to the other term, and we end up with this series, right? And this term, we do the same thing, okay? Now all the series have this power in them. They all start at 0. Now we can factor out the summation sign. We can factor out the rho to the n, or s plus r plus 2, and we're in good business, right? Okay, so here's the differential equation with everything written out. And what you can see is we can write this in terms of this multiplied by this to rho to the s plus r plus 2, right? This all equals 0. What you'll see is there's some straggler terms, the ones we had to run off. These ones, for example, and then there's some more, right? There's this rho to the r, rho to the 1 plus r. There's some terms that are not rho to the s plus r plus 2, right? We had to run off. Now, so that means we're going to end up with 3 separate conditions that have to equal to 0. If I have some expression that has, let's say, if I have an expression, some coefficients rho to the n plus some coefficients rho to the n plus r, 1 plus r, right? 1 plus r and rho to the r. Sorry, some coefficients rho to the r, rho to the 1 plus r, some coefficients rho to the s plus r plus 2, right? These all equal to 0, for example. The only way that this can all equal to 0, it's the same thing as we did the separation, right? This rho to the r, they don't mix with terms of rho to the 1 plus r. So if the whole thing has to be 0, then all of these coefficients have to be 0 independently, yeah? Okay, so let's first start with the rho to the r terms. We collect all the rho to the r terms. Here's one, and so forth. Then we get, for the rho to the r terms, we get this that has to be true for the whole thing to equal to 0. Okay, great. All right, you can, so this is some coefficient multiplied by a function equal to 0. This function is not 0, so these coefficients have to be 0. So here are the coefficients equal to 0. You can rewrite that expression in terms of this product equal to 0. So either a0 is equal to 0 or r equals to plus or minus m. We're going to choose r equal to plus or minus m. Because we need to solve for r, right? Our initial expansion has this r. We don't know what it is yet. We need to solve for it, right? We need that r and we need the coefficients to synthesize f. All right, good. So, okay, so r equal to plus or minus m. Now let's do the rho r plus 1 terms. If we collect all of those, we end up here. And we have this expression in the end. A1 is either 0 or r is equal to plus or minus m. We chose already r. So either this term is equal to 0 or a1 is equal to 0. But we already chose r equal to plus or minus m. So that means we have to choose a1 equal to 0. All right, so remember that r is equal to plus or minus m and a1 is equal to 0. And a0 is non-zero. Okay, now for the r plus s plus 2 terms, if you collect everything, you get this big expression. You can rewrite this expression in this form here. This is called a recurrence relation. But notice, it starts at s plus 2, right? So if I choose s equal to 0, then I get a2. So I need a1 and a0 first. Those are degrees of freedom. So we chose a0 or a1 equal to 0 and a0 non-zero. So we'll see that consequences of that in the next. But once we have fixed a1 and a0, then we can find the rest of the coefficients using this recurrence relation. All right, great. Any questions?
So that's 2 values. So should start to split.
You mean,
We have plus minus m.
yes, very good. A good observation there. So we're solving a second order differential equation, right? So we expect two linearly independent solutions. There are two sets, one with plus m to one with minus m. One of them is an odd series, one is an even series, but we'll see that those two are related. We'll get there. They're related for non-integer m's or integer m's. So we'll have to do something else. We're almost there though. So two solution sets, as you said, one with plus m and one with minus m, right? For the r equal to plus m set, then we have this expansion, f equals to the sum of an rho to the m plus m, right? Okay, so we need a0 and a1 first. We chose a1 equal to 0, so we have the degree of freedom of a0. We're gonna choose that. Once we have fixed those two, an plus 2 is all of this, right? Notice that since we have a1 equal to 0, then all of the odd coefficients have to be 0 because they're dependent on each other, right? Depend on the previous, the recurrence relation. So if a1 is equal to 0, then all of the odd ones are also equal to 0. This is an even series. And therefore, we can let the index, which is n plus 2, there's an n plus 2 here, there's an n plus 2 here. We can let n plus 2 equal to 2k, so it's always even, right? That removes the necessity to keep track of all the odd ones, which you know are 0 already. And k then could go from 1, 2, and 3. So let's do that. A2k now is equal to this expression here. And if you square this out at the denominator, then you get this expression here. Let's run off some of these terms real quick to get a feel for it and what they look like. So here's A2. If I plug in 2 for k, then I get this, right? Beta rho squared, negative beta rho squared A naught. Remember, we still have to pick A naught because k is 2. So, or k is 0 to start, right? Or sorry, k is 2. So 4 minus 2 is, why is it A2k? So 2k is equal to, we start at 2, right? Yes. K is 1. Yeah, okay, good call. Why did I say k is 2? K is 1, right? Sorry, k is 1. So then we have negative beta rho squared, A0, 2 squared, we have k, which is 1, into 1 plus m. All right, let's do A4. The only thing that changes here is 2 and 2 plus m, and then A6. Okay, so we can rewrite this as 2 to the 4th by expanding this denominator, right? We have 1, so we can incorporate the previous result, right? Because we have A2 here, yeah? But we know A2, because we solved it. Incorporate the previous result and rewrite it in this form. The reason why we're writing in this product form is trying to identify a pattern. So then we can generate another expression that will allow us to calculate these coefficients quickly. Same thing with A6, we can incorporate A4, which we solved for, and A2K in general by identifying the pattern of these coefficients, all right? Okay, so we still have everything as a function of A naught, all of the coefficients, right? It's customary to set A naught equal to beta rho to the m, 2 to the m over gamma 1 plus m. Gamma is called the gamma function, and it has the property that we want to utilize of it is that gamma 1 plus m is equal to m times gamma m. It's like the factorial function. Okay, great. So yeah, this is a little bit of mathematics, right? Don't get hung up on the details or get lost. You can always refer to this when you want to understand this. The whole point is that we've solved it once and we know where this comes from at the end. Then we're going to use this, all right? So I don't know if you're following along, that's great. But if you're getting some lost in the details, then don't worry. You can come back in and check this. And the whole point is we want to identify this function. We're going to study the properties of this function in depth, right? And that's all we need. Okay, good. So if we take that expression, this thing here, and write it in terms of the gamma function, then it will look like this, right? And furthermore, we have 1 plus m, 2 plus m, k plus m, and then gamma 1 plus m, which is n times gamma. Oh, no, I'm sorry. This is what we did. Okay. This A0, we've replaced it in this expression here with our assumed expansion here. All right? And we have the gamma function, our expansion. We can use this property to write all of these terms in terms of 1 gamma. Okay, now we have found our coefficients that we are trying. So what we've done, we've taken this here. We've taken this power series. We have a differential equation. We know that probably we can't write down a simple function to satisfy all the derivatives and the relations between them. So we've assumed a power series expansion. We needed to find these coefficients, right? Once we do that, we add up all these terms and we synthesize this function that has the right derivatives everywhere. Okay, here it is. F n equals to 0, an rho to the n plus m. So we've now changed the index k with a 2k because we know all the odd coefficients are 0. And we then plug in what our 2k is and we get this. Okay, this is the grand finale result, right? This is some series expansion for our function f, all right? Now, you will rarely see this, right? Because this series expansion is used so much in physics and engineering that they've given it a special name. Yes?
Should the Bessel function not also contain beta?
It should. That's an excellent, very good. Glad you're paying attention. Very nice. Beta rho, right? Very good. Mathematicians probably won't have this, or they'll absorb it in a different coefficient. So very good. Yes, this is a function of beta rho and rho. Okay. So when sine and cosine were first tabulated, they were a table too, right? There was some kind of relationship between the legs of a triangle. And they've used it so much that they've given it a name, sine, cosine. And you can evaluate sine and cosine, or you memorize the tables, what you're doing. You memorize the relationship between the ratio and the angle, right? The same thing with this. So you don't have to bust out the calculator and add up this series all the time when you want to use this function. It's been tabulated. It's popular enough that now it's been given a name and software packages have it, right? But in the end, it's a table. And in the end, it has the terms in the table are found with that series. All right?
Bessel coefficients compared to Fourier series coefficients in how they, because Fourier series coefficients are for where you label where the exponents are. But the Bessel series is only even.
Very good. So, okay. So a Fourier series is an expansion in terms of harmonic functions already. Coefficients, unknown, sines and cosines. I add them up, I can synthesize any temporal function, for example. This series is a different kind of series. This series is synthesizing a power series function. In the end, this is a harmonic function because we're solving harmonic Maxwell equations. So this has oscillation to it, right? It has some kind of spatial frequency. So this is like a sine and a cosine. So if you wanted a Bessel series, then you would need A and JM rho, right? You need to add up Bessel functions, a superposition of Bessel functions, because the superposition of the solution of a differential equation is also a solution. So that's Bessel series. Okay, great. So here they are plotted, right? Yes.
So if you have a cylindrical waveguide and rho is not allowed to be 0 because maybe there's a section of the center taken out, is it sufficient to just make a change of variables so that rho equals that radius that's missing?
You could possibly do that. That's not the strategy taken here. We're going to derive another solution which has. So what you'll find is a lot of these functions are singular at the origin. By nature, Frobenius, right? We expect them to be that way. Some function that has one over rho, for example, when rho goes to 0, that goes to infinity, right? So this is still a valid number here, but if it has to be finite, then we'll see the 0th order Bessel function, the m equals 0 is the only one that's finite at the origin. So you can still use rho equal to 0 is what I'm saying, but you just have to be cognizant of what your expansion functions, the properties of them are at rho equals 0. So we'll have practice doing that, right? I'll show you. Okay, great. So here are the functions, right? So we can also do the same thing for r equal to minus m solutions, analogously, and we end up with f of beta rho rho is a1jm plus b1jm minus m, all right? Where m is an integer. All right, so then here's the two solutions, the expansions. The problem is that if m is an integer, then jm and j minus m are linearly related to each other with this property here. Problem there is they're linearly dependent solutions now, and we need two independent solutions for our second order differential equation. So we need to construct another solution. All right. Okay, if m is not an integer, which happens in spherical coordinates, we're going to use these same functions in spherical coordinates, but they're half integer orders. Then we're okay with these two solutions. But if we have integer order m's, then they're linearly dependent, and we have to find a third solution. And this solution is the one that you derive. You also might see this in your homework, right? The derivation. This is Bessel functions, the second kind. So these are called first kind Bessel functions. These are called second kind Bessel functions. And the property of Ym is that it's singular at the origin. So I plotted both of them here. So just like sine and cosine, right? We got sine and cosines and exponentials in rectangular coordinates. Here we also have the similar behavior. It looks sinusoidal, but it's damped, right? And this one looks sinusoidal and it's damped. It has different behavior at the origin, right? Like we were kind of noting. But you'll get used to the properties of these functions, utilizing these cylindrical expansion functions to solve problems in electromagnetic theory. At the end of our course, we're going to do scattering chapter, and we're going to utilize these heavily, right? And so we got to get used to understanding when they're applicable and what their limitations are and so forth. And we're going to do that. Okay, so this is another solution which you can get, and you'll probably do that in your homework. So the general solution for not an integer, I think this is backwards, right? Sorry. So this is m is not an integer. Yeah, this should not be not, right? This should have not. Make the change. I'll verify it though, but I'm almost positive. Okay, so now here's our solution, Jm and Yn, right? So our solution now is in this form, which is kind of nice. It's like a cosine plus b sine, like we had before. We just have Jm and Ym. We just have, remember how in the course I've been stressing when you see upside down triangles, to not think of them as something mysterious or new, think of them as spatial derivatives, partial by partial x, partial by partial y, which you've seen 100 times. As soon as you make that connection in your mind, these expressions don't look scary that involve curls and divergence. Here, we're going to make the assignment that Jm and Yn are some functions. You know what cosine and sine are, right? You've plotted sine and cosine before in your previous mathematics courses. And as soon as you see sine or cosine, you know exactly what it looks like, you know, it's all its properties and everything. You're going to get just as familiar with Jm and Yn. All right, so just think of them just like you would cosine and sine, but they're expansion functions in the cylindrical coordinate system. So here are some of its properties. If you plot them, all the Yms here. So as you increase the m, you get different terms, right? So that's one difference between sine and cosine. These have different orders, right? So these are Bessel functions of a particular kind, the first kind and the second kind of order n. All right. Now it's not a mystery that this has order m, right? Why do we choose, or where does m? Where have you seen m before? Where? Yeah, so, okay, it's kind of a vague question, right? Remember I was saying, okay, there's some linking between the expansion functions in azimuth and in row, because Bessel's differential equation had an m in it, right? It's not on the slide. It had m, which was our separation constant for phi, right? Here, it has the m in it, and m is our separation constant for the azimuthal modes. So, as I was saying, these functions, once you pick an azimuthal order, say, so you're expanding some, I'll show you some expansion on the next slide, what they look like. But you choose an azimuthal order as one of the terms in the expansion, then it fits your order of your Bessel function. Then you only have 1 degree of freedom of beta rho. Okay, as you increase the order, these functions have, this property here. You can visualize them there. J0 is the only one that's finite at the origin. And then all the rest are non-zero and finite. So J1 and J2 are all 0. All the higher order J's are 0 at the origin, except for J0. And all of the Yms are negative infinity at the origin. Okay, good. Yes.
Non-zero. How does the general function handle Williams or not rational numbers?
If m is non-zero.
I mean, if n is not an integer.
Okay, yeah. So there's an analytic continuation expression that you can use, or an expression that you can use based on analytic continuation to extend the gamma function into non-integer order into the complex plane. We don't need that. We might for the spherical coordinate system, but when we get there, we'll discuss that. Yeah, but yeah, good thinking. You want to start thinking about the bounds of these expressions and how, you know, where you can push them, where their validity is, and so forth. So it's a good way to think. Okay, remember the three functions we had in rectangular coordinates were cosine, sine, and exponentials, and we identified sines and cosines as standing waves because when we multiply by either j omega t, take the real part, then we end up with a function sine that doesn't have the form f of x minus vt, which was our wave solutions, right? The solutions that we showed that move to the right have to have an argument of x minus vt. Exponentials do though, because e to the plus j beta xx and then e to j omega t, you can combine those two before you take the real part, and your argument is beta x minus omega t, right? Okay. By Euler's identity, we can add two standing waves that are out of phase by 90 degrees, and we can synthesize a traveling wave, right? Okay. That's by Euler's theorem, right? So the sinusoids are real valued, however, the exponential function is complex valued, right? So these two standing wave solutions, we add them together with the 90-degree phase delay. I guess it's not necessarily 90, this is already 90, right? So it's 90 plus j. Sine and cosine are 90 out of phase, and then we have j there as well, bringing it back into phase, or 180 degrees out of phase. So we get an exponential, a traveling wave from that, right? Same strategy in cylindrical coordinates. I'm going to take my two standing wave solutions. I guess we haven't said that these are standing wave yet, but they are. Take these two standing wave solutions, add them together with the 90-degree phase delay here, and I get a traveling wave in cylindrical coordinates, all right? The same exact approach. This traveling wave, there are two kinds. They have a new superscript. So before we had Jn and Yn. Now we have two kinds of these, just like we have plus and minus traveling, right? Depending on if I use plus or minus here, they could travel to the right or to the left. Here, if I use plus or minus, they could travel inward or outward, all right? And to distinguish the two, we have a superscript 1 or a superscript 2. Okay, when you drop a rock into a pond, these ripples, these rings, they travel outward. That's a traveling wave in the form of a cylinder. It's a cylindrical wave. It's a traveling wave outward, right? Those are described by these Hankel functions, all right? So if you choose the minus sign, you get the outward traveling wave, which is one we're going to use a lot more.
So it's a special function where we only have row dependence.
Yeah, this is only the row dependence, right? I'll show you on the next slide. To get to the actual electric field, we need rho, phi, and z dependence, right? For one of the scalar components of the vector field. We'll get to that next slide. But yeah, this is row dependence only, right? Okay, so similarly, these are real value functions, j and y. When I add them together, I get a complex valued function called the Hankel function. So don't be afraid of the Hankel function either. It's just like exponentials, but in the cylindrical analog. All right. You just have to use them more or less. In the end, you're going to write a MATLAB code that you call Bessel H, and you evaluate it for n and 2 and beta, and then you add a bunch of them together when we get to the scattering by mode matching. All right. Okay, great. What do they look like? Oh no, one more. We also have, in addition to standing waves and traveling waves and rectangular coordinates we have evanescent waves, right? So the evanescent equivalent in cylindrical coordinates are called Bessel functions, the third kind, or modified Bessel functions, all right? So modified Bessel functions are I and K. So you have J, Y, which are the standing waves. You have H, 1 and 2, which are the traveling waves. And you have I and K, which are the evanescent waves. And they look just like what we'd expect, right? And they have this form here. So you take a combination of exponential function. Do you remember what happens when you take a sine function and evaluate its argument as a complex number or an imaginary number? What is sine of jx? You get hyperbolic functions, right? Sine of complex arguments or sine of imaginary arguments are hyperbolic sine and cosine, which are also evanescent waves, right? Same thing here. You evaluate these functions with a complex argument like this, and you get evanescent behavior out of it. All right, great. So here's some properties involving Bessel functions, which you can refer to when, or modified Bessel functions, which you can refer to when solving problems. And here's the plots of i's and k's, right? They're exponential decays, like you expect. So let's put all these into a table. We have traveling waves are our Hankel functions, which are constructed from Bessels, added together with some phase delay. Okay, so they travel out to infinity, and there's infinities and zeros of the wave functions you can plot, right? Or you can identify. Standing waves, J and Y, right? And there's infinities of these, right? These are actually important. You need to know the zeros of the Bessel function when you want to set, say you have sine of n pi x over 2 is equal to 0, right? N pi x over 2, sure, equal to 0, right? Then you need to find all the zeros of the sine function to solve for, so maybe we need n pi beta over 2 or whatever, right? You want to solve for beta, you need the zeros of the sine function. You need the zeros of the Bessel functions in the similar analogous situations. There's a table of them. Or you go to MATLAB and you type in to give you the zeros for the Bessel functions. Evanescent waves, we just saw those, K and I, right? And then if you add combinations of evanescent on top of standing, then you can make attenuate, or evanescent on top of Hankel, you can make attenuated traveling waves. So now we have a complex number here, not just imaginary, as the argument to the Hankel functions. And that's just like your damped sinusoid. Sine times e to the minus x, right? E to the minus alpha x times sine of beta x, which was the damped sinusoid. That's these. And, or these is probably more better than the situation. Attenuating standing waves, right? Okay, good. Any questions on those?
So the zeros of the wave functions are complex omega, or are they out at infinity? Or
The zeros of what?
the zeros of the traveling waves are out at infinity if we look at the.
So this is called the radiation condition. If it's a traveling wave and it's carrying power away from some source, then the power has to decay at infinity. It's a radiation boundary condition. So that's what they're saying here. These functions don't go to 0 until you go out to infinity.
So when we take the real analysis where we're integrating overall infinity.
Yeah, in that sense, if you're integrating some function in the complex plane that goes to 0 at infinity, then you can ignore the upper hemispherical path of your closed path to apply cylindrical theorem or whatever. Yes. But this is different, right? You want your power, remember, if I have 1 watt of power here, and I integrate and I cover this thing, I surround it with a sphere of radius A, and I add up all the power along that sphere, right? I should get 1 watt if the medium is lossless, right? 1 watt of source being supplied to the medium from this source, 1 watt of power being supplied by this source to the medium. I cover that whole source with a radius A of sphere. I add up the power by integrating the power density on the surface of that sphere. I get 1 watt, right? Conservation of power. If I go to 10 times A radius sphere and I integrate the power density around that bigger sphere, I still get 1 watt. But that must mean that the power density is much, much less on a bigger sphere, right? So you guys see what I'm saying, right? 1 watt here, I have a small sphere. The power density is larger than on that surface of that sphere because that surface area I get from integrating that sphere is less than a bigger sphere, which means the power density has decreased. As a matter of fact, that's why the power decays is 1 over r squared, because the surface area of a sphere grows proportional to r squared, and power must be conserved. We saw that. I had a slide on that, right? Okay, good. So here are, remember, what did we do when we solved the wave equation? We said that Z has to be Z, right? Let's make it psi so we can make it general. Psi, Z of rho, phi, and Z could be F of rho, G, phi, H, Z, right? That was my assumption in separation of variables. We now identified all of these, F, G, and H. And these are the strings of functions that you put together to synthesize psi, which could be any z-directed field quantity or any z-directed potential, vector potential. All right. Practice is what we need to really drive these concepts. So you'll use these a lot. I put them on the slide. You can refer to them when you do your homework. Large and smaller human expansion and derivatives. So if x is very small, then you use this expansion for j0, y0, which is jm f, right? Which was j plus y. So if x goes to 0, then we only have the 0th term, small argument expansion, and we can approximate it in this way. When j goes to, or when x goes to 0, we have the same expression here. When x goes to infinity, they look like sinusoids, cosine and sine, right? With respect to rho, but I guess this is an x, right? And they have a dampening 1 over x, 1 over root x. Why 1 over root x? Based on what I just told you with the spheres. Let's draw it. So here, source here, right? Here is a sphere, a cylinder now of radius A. Here's another cylinder of radius B, right? Now these cylinders are invariant in and out of the board, right? Let's say this is a 1 watt source. I have some power density, which is S, right? On that sphere from E cross H conjugate, 1/2 real part. I integrate that power density over this whole sphere. What should I get? If I'm integrating the power density over an area, I get power, right? What power should I get? 1 watt, right? Okay. What in rho, how does this surface area grow in rho? Okay, let's do a 2D problem, right? Let's do 2D. So forget about in and out of the board. These are circles now. What is the circumference of the circle? C equals to 2 pi rho, right? Okay, so the power, in order for me to get 1 watt here and 1 watt here, then the power has to decay. So the power, S, has to be proportional to 1 over rho. Why? Because in any sphere I draw, any circle that I draw, I still get 1 watt of power because that integration result has to be independent of what size circle that I choose, right? If the power has to decay as 1 over rho, and the power is proportional to E cross H, or you can think of the units as E multiplied by H, right? Forget about the vector direction. Then each of these field components have to decay as 1 over root rho. Because I'm going to multiply them to get power, and I get 1 over rho then no matter what circle I choose, its surface circumference grows with respect to rho as rho, right? Proportional to rho. The power decays with 1 over rho, then my power that I get is independent of what circle I choose, right? Okay, good. There's derivatives here, and there's these large argument expansions of the Hankel functions, all right? Any questions? All right.
Derivative of Bessel function is a difference of orders.
Yeah, very good. You reduce the order or you increase the order, depending on which form you pick. And it's a superposition of the two, yeah.
So it becomes a difference equation.
If you were to treat it in a discretized sense, yeah. What will happen is you're gonna need to differentiate these Hankels when we get to scattering. So just apply this formula. If we did it in a discrete derivative way, finite differences, then it would be a difference equation. Great, so let's see what they look like. Here's EZ, right? Remember it's a Z component or a Z component. I've chosen J0, e to the j and phi, e to the minus j beta z, just for illustrative purposes. I tried to plot these. I wanted to give you guys a visualization of what these might look like. Now looking back, this might not be the best way to see it, but you need to see the product of these three things, right? Because that's what EZ is. So here, M is 0. So remember, you pick these three independent eigenvalues, right? The three eigenvalues are M, beta, Z, and theta. Beta rho is not independent, right? If I pick beta and beta Z, then beta rho is defined. Because beta rho squared plus beta Z squared equals to beta squared. And beta squared is omega squared mu epsilon, which is our which is dependent. So beta rho squared, beta z squared, beta squared, which is omega squared mu epsilon. Once we choose the frequency, time harmonics, we have a single frequency, everything's linear, no new frequencies are generated. And we have a medium, mu and epsilon, then the product or the summation of those two betas have to equal to that. Okay, so beta z is pi. So we expect e to the minus j beta z that this thing goes through some variation in z, right? So we can see okay, so what am I plotting here? One cylinder. So on the surface of the cylinder, you can see z variation. I'm plotting a plane here to show you the rho variation. And then the azimuthal variation you can also see on the surface of the cylinder. All right. Why can't I just use the cylinder to show you these? Because beta rho is constant on the cylinder. You can't see its variation. So you have a cylinder to see azimuth and z, and then the plane shows you rho. So here's rho. Look, rho looks like a kind of a sinusoid. And we have some sinusoid in z, and then azimuth is constant. There's no variation in azimuth, right? Because m is 0. Here's one where m is 0, but a higher frequency now. So we have more variation in z and more variation in rho, right? Yes. All right. Here we have some azimuthal variation added to the z variation gives us a spiral. I don't know if these help you or if they might not.
With Bessel function.
M. So remember, once we pick azimuthal variation, the order of the Bessel is fixed. So this has no azimuthal variation, right? So what is the Bessel function? That's J what? J0. Very good. It's J0. This one is also J0. This one is J1, right? How can you, I guess you can't see it because we're not playing at the origin. Okay. So what was your question?
What was physical?
M tells you that, look here, e to the j m5, right? So as m increases, integer m, the phi variation increases.
So it's like a spiral into the center.
No, it will just give you on the surface of a cylinder. If it's constant, then my field value does not change when I change an azimuthal variable phi. If I have one variation, either j phi, what'll happen is the function will go through one, so it'll go from a max to a min back to a max, right? As you go in azimuth, which is this, but then you add the z, so it starts to look like a spiral. Okay, why am I showing you these expansion functions like this? When you solve a problem in scattering or so forth from cylindrical coordinates, you're gonna express or expand your function in terms of summation of all of these, right? It's going to be a summation of JMs and e to the JM phi and e to the minus j beta z. Rarely will a solution to a scattering problem be one of these. It's going to be a superposition, a weighted combination of all of these modes that you're going to add together, all right? So here's one with, right here, the azimuthal variation. You go from a max all the way back to a max when m is equal to 1. But there's no z dependence now, right? So you have constant in z. And you still have your beta or your rho variation. Here we have m equal to 2. So you go min, max. And then here we have another combination, okay? All right. That's kind of what they look like. I was trying to figure out how to show you the variations, but okay. Let's do an example. Cylindrical waveguide. Okay, so as I was saying, if you have, what is a waveguide? If I am talking to you guys in the room, the acoustic wave travels outward in all directions, right? Therefore, I can broadcast all of you, but I have a certain amount of power that I have to spread throughout the room, right? But if I wanted to talk only to one person, then rather than me wasting power in directions orthogonal or away from the intended receiver, I can guide my energy along a path, like a wrapping paper tube that you've gone through in Christmas. There's no wrapping paper, toilet paper tube, or paper towel. If I talk into that, then all my energy is directly to the receiver, right? I'm guiding the wave instead of letting it diffract. So in doing that, I apply some boundary condition. This is exactly like that. If I put a source in here, the energy will be restricted to travel along this path defined by the waveguide. It's just like me talking and launching an acoustic wave into a wrapping paper tube. So what does the solution to that look like? Here is psi, rho, phi, and z, right? For some component of the field. We know what component must this be? I just say psi here, but what do we know about solutions in cylindrical coordinates? This has to be which component? Z. Very good. Very, very good. That's very important. You have to think, you have to remember that. But a lot of times in cylindrical coordinates, you have an axis of symmetry, which is the z-axis. So this kind of, it's not very restrictive. All right, so F, G, and H, right? So here's our full F, full G, full H, right? Now what we're going to do is figure out what these unknown coefficients are and the eigenvalues beta, rho, m, and z. So applying the boundary condition, okay, first, why did I choose, in rho we had Hankel functions as well, right? H's, but we didn't choose those. We chose J and Y. Because in rho, what do we expect? Remember, PEC reflects like a mirror, right? So in the rho direction, I have a mirror here and a mirror here. I'm just going to get some wave bouncing back and forth, right? Which is a standing wave. So I expect standing wave, not traveling. You can't travel. It's going to reflect back and forth. So these are standing waves in rho, which are J and Y. So already I know to choose J and Y. I don't know A, B, or beta rho yet, all right? And we have periodic functions in phi, so cosine and sine, right? And then traveling waves in z, it's unbounded. There's no discontinuity in z. So we get e to the minus j beta z, e to the plus j beta z. So we apply boundary conditions to find the wave numbers and most of the coefficients. For example, the fields have to be finite at rho equal to 0. I can't have some expansion of an electric field which is continuous and finite that was generated from a finite source have an infinity at the origin, right? So for sure, my field expression that I'm expanding psi in terms of these wave functions, right? And it cannot be singular at the origin. So we know which functions are out. Okay, if you have a delta, okay, so a delta can be modeled as a finite function, like a Gaussian that goes to 0.
It can't be infinity.
Has finite area. Yes, you probably need a lot of expansion functions to synthesize that, but let's assume that we're not working with delta function yet. We have some field here that's continuous log behind. We know that J0 was finite at the origin, J1, J2, J3 were finite. J0 is 1, all the other J0s or JMs are 0. But YM was infinite, right? They were minus infinity at the origin. So we know that we have to have B1 equals to 0 because YMs are infinite at the origin. So we end up with this because all YM are singular at rho equal to 0. Okay, so, and then we have these expansions, which we'll have to determine using the properties of waveguides, which we'll get to. If the problem was scattering from the cylinder rather than guided waves within it, so instead of having a source in here and launching waves down the cylinder, I have some source out here, which is launching a wave which scatters from it. If that were the case, then we wouldn't have finiteness in rho, right? Because this in rho, they're going to reflect, give you standing waves. But this wave that's traveling here and reflects off, this is a diverging or expanding cylindrical wave that travels away. So we'd have Hankel 2, right? Hankel 2 because they travel outward, and Hankel because it's a traveling wave, right? My scattered wave, I'd expand in terms of Hankels. We'll do that later in this course. Okay. All right. All right, so you guys are now experts in solutions of the wave equation in cylindrical coordinates. And if you haven't seen that before, you should feel pretty cool because first time I saw Bessel functions and the solutions to that, especially applied to electromagnetics problems, made me feel like I knew something, right? Which is cool. So tonight when you're eating dinner with your significants or your pet family, you can tell them that drop a little seed in your water cup and tell them, you know, exactly what describes those ripples on the surface of the water, all right? Make you look smart. That's what we're here for. All right, so now we're gonna do the same thing. I'm wondering if I should launch into, we have 5 minutes. Let's just go into it and we'll come back and start here again next lecture. So we're gonna do the same thing in spherical coordinates. Now remember, what is the difference between rectangular and cylindrical coordinates? We still have 2 lengths. In rectangular, 3 lengths, right? and we introduce one angle in cylindrical coordinates. So we still have rho a length, z a length, but now we have an angle phi. By introducing an angle, we introduce scale factors so that we can talk about lengths again. So d phi times rho gives you an arc length, right? So we have to introduce all these extra scale factors. Now we're going to do it one more. The difference in rectangular and spherical and cylindrical and spherical is going to add another angle. So we only have one length, r. Now there are two angles, theta and phi. And that's going to make things even more difficult. All right. In spherical coordinates, we have the variables r, theta, and phi, right? We know that. R, theta, and phi hat components that each have their own scalar function, which tells you how long the r part of the unit vector is, or how far the r. Okay, so E of r, theta, and phi. You give me an r, theta, and phi, this point. I will give you a vector there. That vector has an r component, a theta component, and a phi component, right? To find what those three components are to add together to give me the vector at that point, I need to evaluate these three scalar functions at that point. E r, E theta, and E phi. All right. Do the same thing. We take del squared E, we express it using our favorite identity. We plug in E and we get these three. What are we going to do now? They're all coupled. This is a mess. Why are they coupled? We're supposed to end up with three scalar PDEs that are hopefully functions of only one component, right? Here we have ER, we have E theta, and we have E phi. So it's coupled, all three of them still, right? All of these have ER, E theta, and E phi. That is very difficult to solve. And we're not going to solve those, right? So you cannot separate this into, the vector-Helmholtz wave equation cannot be separated into scalar PDEs in spherical coordinates. So we have to find an alternative approach. No. Okay, this is a system of 3D equations and three unknowns, which you've probably seen in like linear algebra, but these are differential operators. It's systems of three differential equations, even worse, the partial differential equations of multivariate functions, with three unknowns being the multivariate functions. So that's the approach we'd have to solve them in that way, right? We're gonna avoid that though. I think it's gonna be a mess to try to attack that. But luckily there's an alternative approach and it's based on auxiliary vector potentials. So I'm gonna preview them here and give you all the necessary information you need to understand and to construct solutions in spherical coordinates. And we'll get to utilizing the vector potentials to solve inhomogeneous forms of the wave equation later in the course. But here you're going to get a preview of it. And let's see. Okay, so why don't we end here? This is where the class gets exciting though. It's kind of bumming me out that we have to end here. But we'll come back to this Thursday. You're going to get a new homework on Thursday, right? So make sure you start it early if you know how long it takes. And again, don't forget we have that one rescheduled lecture, and that's it. I have office hours today as well in like half an hour, so come by if you guys need it, or you can do the Zoom. All right? All right, guys, very good. See ya. Well, if any of you want your homeworks, I don't know, I'll have them in my office too. These are the ones that you didn't collect last time I handed them back. You got, okay, yeah, homework 1.
Oh.
Homework 2 is not done yet. Homework 1. You did? What's your name again? Oh, Tristan, how are you doing?
Actually, sorry.
Oh, you did? Yeah, when I was making the notes, I was like, how can I see if you can visualize these? They're kind of hard to visualize. All right, very good. I don't see it here. You didn't get it yet? Okay, yeah, you must have. All right, very good. Not that one, yeah? Nope. Okay, good. All right. Oops.
Have a good one.
All right, have a good one. See ya. How's it going?
Hey, Jordan, very interesting.
Oh, wow, thank you.
I mean, interesting to the extent I haven't done this kind of math in a while, so it's good for me to play catch up.
Oh, very good.
Yeah, I like the math aspects. Get to do it very much in my computer engineering world. So-
Yeah, I did look your Scholar, Google Scholar up, your AI and computer vision and all that, right?
Right,
Very nice. That's very interesting stuff too.
very interesting. I'm going to take off, but great to.
All right.
This one.
Yeah, thank you for coming.
Assisting or tempo. Did you just come from book or? Yeah, I came from book. You also? Yeah. I was about to call you, so when I looked, I turned right and I saw you. I said, "Oh, that's it." No, I came here at 10:40. Then this class was on. I came here at 10:40. Oh, that then just for a few minutes. When I came, I went to sit at the other side. So what about your project technical security? We are meeting today. Yeah, meeting is like implementation will be a bit hard. So, but the lady says she has done it. Yes, they are going to do the machine learning thing, but me and the other boy here, we are going to do another like use a statistical based method. We have selected a database, but for that particular database, there is no statistical methods. Like we may need to develop our own and maybe by looking at something else. Because machine learning is just applying that, right? But statistical based, like maybe we need to have a good idea about the protocol. Yesterday, whole day I was working on that, so I'm not going to work on that today. So,